Today we're going to be talking about properties of functions. These are very important to be able to identify, especially as you get into contextual problems or problems in calculus. Next lesson you'll be learning how to minimize and maximize, and so identifying those points will be critical. At the end of this lesson, you should be able to identify all those points, as well as graph functions over given intervals, and determine function symmetry. Let's start by identifying these key properties within a function. Here we have a graph of a sinusoidal function that goes from negative pi here to positive pi. This is our interval upon which we have graphed it. If you are to graph this in your calculator, you'll see that it continues to wave over and over again, but we just want to examine the interval between negative pi and positive pi. So let's first identify the intercepts. Well, our intercepts are going to be both the x and y intercepts. Well, we have an x and y intercept here, we have an x-intercept here, and another x-intercept here. So what we would do is list those intercepts as coordinates. And here they are. We have 3 intercepts. Those are important when we're determining solutions, finding solutions to functions on graphs. Now let's think about our domain and range. We already talked about our domain. Our domain is going from negative pi to positive pi. But what about our range? Well, our range is going to go from our minimum point here, which is down at -1, all the way to our maximum point up here, which is at +1. So sometimes it helps to identify your local minimums and your local maximums prior to finding your range. Let's go ahead and write our domain and range in interval notation. Remember, when we write it in interval notation, we use brackets if we include those numbers, and these are all included in our domain and range. Let's look at C, intervals, which is increasing, decreasing, or constant. What that really means is we're looking at our slope along our domain. So between negative pi here and negative pi over 2, what is our function doing? Well, our slope is decreasing. And then from negative pi over 2 all the way over here to positive pi over 2. So basically, between negative pi over 2 and positive pi over 2, our slope is increasing, our function is increasing. And then once again we have a decrease from pi over 2 to pi. So let's write out those intervals. Here we have our intervals written out. These intervals, remember, are just your x values. We're just looking along our domain to see where our function is decreasing, where it is increasing, and where it is decreasing again. So always remember to think about this in terms of your x values. How about our local minimums and maximums? Again, this would be something that would be beneficial to find first to help us find our domain and range, as well as to help us find intervals of increasing or decreasing. Well, our local minimum we said was down here at negative pi over 2, -1, and our local maximum was here at pi over 2, 1. After jotting these down, then we can move to symmetry. Now remember too, with the minimums and maximums, these points are going to be important as we move forward into the next lesson, because these points will help us determine our minimum amounts or our maximum amounts. Let's go back to symmetry. We want to determine if our function is even, odd, or neither. Graphically, it's easy to determine. If it's even, that means we can fold this paper right down here along the y-axis, and this side should have a mirror image to this side. But you can see that that's not the case. We don't have another function that looks like this right over here. So picture this being a big mirror right here down the middle, down the y-axis. So we know this function is not even. If it's odd, however, then our function is symmetric about the origin. In other words, a graph should look the same whether it's right side up or upside down. That's what it means to be symmetric about the origin. Another way to think about this is that the graph should remain unchanged if you reflect it across the x and the y, both. So if we reflect this across the y and then across the x, we will get this same curve here as we did here. So you can picture taking this curve, reflecting it over the y, and having the curve look, well, not quite like that. Let's try that again. Having the curve be here, and then reflecting across the x-axis, the curve would then drop down below So this graph you can clearly see looks the same whether I turn it 180 degrees or leave it as it is, upside down or right side, or if I take this and reflect it across y and then across the x. So this graph is certainly odd. Another way to think about this is algebraically, and we'll be looking at that in a minute. But basically, it's even if you can plug in a negative x into your function and the result is the original function. It is odd if you plug in a negative x into the function and the new resulting function is the exact opposite of what you started with. In other words, the signs are opposites of what you started with. So if you have a positive, it's now a negative. If you have a negative, it's now a positive. Let's look at another example of identifying properties in functions. In this example, we want to graph this function, y equals 3 times the sine of x minus 1 over this interval, negative 3 to positive 3. And you can see that I went ahead and put this in my calculator from negative 3 to positive 3. Also, what's very helpful in your calculator is to identify the intercepts. Your calculator can identify those for you, as well as the local minimums and the local maximums. You can also use the Desmos.com calculator, and all you have to do is click on these spots in order to call up these points. So our intercepts are here, negative 2.142. Our y-intercept is here at negative 2.52. We have another x-intercept here at 1. So we have our intercepts. Our domain, well, that was listed for us. That was from negative 3 to positive 3. And again, brackets, because we are including the negative 3 and the positive 3 in our domain. Our range, on the other hand, we need to look at our minimums and our maximums. So our minimum goes way down here at negative 3, and our maximum is way up here at positive 3. And again, those are included. So we have negative 3 to positive 3. We have the same range as we do our domain. The intervals upon which this function is decreasing, if we go from left to right so we can keep things in order, from negative 3 all the way to our local minimum here of negative 0.571, we have a decreasing function. So we can write that as negative 3, and we're just writing the interval. So this isn't interval notation used to describe domain and range. We're just writing the interval upon which this is decreasing. So from negative 3 to negative 0.571, we have a decreasing function. And then from this same minimum all the way to our maximum, we have an increasing function. So we increase from negative 0.571 all the way to this point here at 2.571. Notice I'm looking only at my domain when I'm determining whether it's increasing or decreasing as far as labeling it, the intervals. So I know that from negative 3 here on my domain all the way down to negative 0.571, again on my domain, my x values, my function or my slope is decreasing. We have one more here. We can see that our function is starting to decrease on this interval from 2.571 to 3. And because this is graphed only between negative 3 and 3, I don't use infinity. I'm just concerned with the domain between negative 3 and 3. How about symmetry? Well, we know it's definitely not even because if I fold this, I'm not going to get a mirror image of this side over here. How about odd? Well, if I take and I flip this upside down, does it look the same? You can see that it's close, but not quite. So this is neither. Finally, we get to our local minimums and maximums, which we've already identified earlier as here is a local minimum and here is a local maximum. Let's conclude our lesson today with looking at algebraically whether a function is even, odd, or neither. Let's look at the symmetry. Here we have a quadratic and I've graphed it. And you can see very clearly that this is an even function because if I fold this along the y-axis, what I see here will be a mirror image over here. But say we didn't have the graph or we didn't graph it and I was just given this function. Well, remember that we can plug in a negative x in for x and simplify. So let's do that. Let's see what we get. we're going to plug in a negative x for all of our x's. So we would have negative x squared plus 4. Well, think about what we have here. So if we plug in a negative x squared is going to be positive x, and we're going to still be left with negative 3x squared plus 4. Remember what I said earlier. If you plug in a negative x into your function, and your result, which is right here, is the same as what we started with, then we know that we have an even function. This result is definitely the same. Let's look at another example. In this function here we have a cubic, and here's a typical cubic pattern. And we can look at this and say, hey, if we flip this around 180 degrees, what we started with looks like the same thing 180 degrees later. This is very symmetric about the origin. So we know it's odd algebraically, but let's prove it, or I should say graphically, but let's prove it algebraically. So again, we're going to take our function, we're going to plug in a negative x for all of our x's. And let's see what happens. So here we would have 2 times negative x cubed minus 4 times negative x. Let's simplify that. In this case, a negative x to the third power will still be negative. So we'll be left with a negative 2x cubed. And negative times a negative here is going to give us a positive. Let's compare our functions. Well, we started with a positive sign here, and now we have a negative. We started with a negative sign here, and now we have a positive. So if we can plug in a negative x and get the opposite result, so now our whole function is negative, so f of negative x is equal to negative f of x, then we've proved that our function is indeed odd. And that concludes our lesson today on properties of functions. At this point now, you should be able to graph a function between a given interval, identify the intercepts, the domain and range, as well as the intervals upon which it is increasing, decreasing, or perhaps constant, any local minimums or maximums, and finally the symmetry, both algebraically and graphically.